for inviting me. And I can say it's been amazingly well organized in the sense that the amount of overlap from the lectures directly preceding mine to mine has been really great. So today we're going to use, I didn't know it was called the Determinant Method, but some very ideas that were, a lot of ideas that were discussed, at least related to what were discussed in the last lecture. Okay, so today's goal is to prove a theorem of Waltzman, which I stated last time. Actually, before I do that, I used this lemma last time when I was proving the equivalence between the structural rank conjecture and the special case of Shanuel's conjecture. And so I just want to give a proof of this as a result of Damien Roy, which I said would be a fun exercise for anyone to try to prove last night. So let's say you have a commutative ring, K, and you have a polynomial over that ring in a certain number of variables, n variables. Then there exists a square matrix with coefficients, which are in coefficients that are sort of linear forms in these variables. So you take the sort of K span of the variables x1 through xn plus K itself. And I use the fact that there's a polynomial, there's a matrix with coefficients in here whose determinant is your original polynomial that you start with. So this is surprisingly tricky to prove. It's not completely obvious. So let PD denote the K subspace of polynomials of degree less than or equal to D. Given a matrix with coefficients that are polynomials of degree D, at most D, in these variables x1 through xn, there exists an integer s in matrices. So basically matrices that you can multiply together where one has sort of the polynomial degree has gone down by one. So we're going to use this to do an induction somehow. So if you start with a matrix with coefficients that are polynomials of degree D, then you can always sort of factorize that matrix as a product of two other matrices where one matrix has coefficients that are polynomials of degree 1 and the other matrix has polynomials that are degree D minus 1. Okay. All right, so how do we prove this? So let's say that you start, oh wow. So again, we're having Zoom. I see on the screen, it didn't advance the slide, is that right? Okay. God, I wonder why this is happening. Maybe in presentation mode it's better. Okay. Okay, now it advanced. Okay, good. So so we start with our matrix where the coefficients are polynomials of degree D. And okay, so it's a polynomial of degree D, so you can write it as each element as a sum of some, you can sort of factor out an XL if it appears, and if you sum over all possible variables, then of course you can write it as a sum of expressions of Cij L times XL, and then plus you might have some constant left over. Okay, so theseCijls are polynomials of degree D minus 1 now because you factor out an XL. So this had degree D. So when you factor an XL, it has degree D minus 1. Okay, so then you let Cij be the 1 by n plus 1 matrix of theCijls. And you let X be the vector of your variables, x1 through xn, and the number 1. Okay, and then you define your matrix A to be the matrix you get by taking theseCijl vectors, these are row vectors, and putting them together in a matrix. So the point is that Aij is the product of this row vector with this column vector, so that when you put them all together, you get that your original matrix N is the product of this matrix A times this matrix B. So B is just the tensor product of X with the M by N identity matrix. Okay, so with that, so that proves lemma 1. And now with lemma 1 in hand, then you can prove the actual lemma that I wanted, which is that any matrix shows up as a determinant, okay, by kind of an inductive process. So we have this lemma 2 that if I have an m by s matrix and another s by m matrix, then the determinant of A times B is the determinant of a bigger matrix somehow. But it's a block matrix where I have the identity B, negative A, and 0. And the point of this, just to go back, was that A times B was our matrix that we started with, where the coefficients were polynomials of degree D, and A and B have the property that they're matrices that multiply to this matrix that I started with, but they each have coefficients with degree smaller. So this is degree D minus 1, this is degree 1. And so in this way, I've started with the matrix of coefficients of degree D, but now I've written it by combining the two lemmas as the determinant of a matrix where the coefficients all have degree at most D minus 1. So then you can continue this process until you get down to degree 1, and then you've written your polynomial as a determinant of a matrix where all the coefficients have degree 1. So once you have this limit, this second lemma in hand. And I should mention, this addresses the question that was asked, is the n the same, sort of the degree and the dimension of the matrix, and you can see not. You can see the matrix gets a lot bigger in dimension every time I apply this induction, every time I knock down the degree by 1. So the dimension actually goes very fast. And I should say, there's a huge literature on this in computer science on determining the minimum dimension of a matrix for which you can write your original polynomial as a determinant of a matrix of that dimension where all the coefficients are degree at most 1. So this is a big problem in theoretical computer science that has a very large literature. And in fact, it was a computer scientist that first discovered this lemma. Okay, anyway, so let me now, so the proof of this lemma is just a computation. Okay, so you can conjugate this matrix, whose determinant I'm saying is equal to determinant of AB. You can conjugate it, or I guess not conjugate it, sorry. You can just multiply by matrices of determinant 1 on the left and the right to get a matrix that clearly has the same determinant as AB, namely a block matrix where it's AB and then a identity matrix. Okay, and so this is just a computation. You just multiply this out and you get this. Okay, so that's the proof of lemma 2. And right, and I've already said the proof of the main lemma now. I've already said it in words before getting to this. So right, so we start with any m by m matrix with coefficients of degree at most D, in particular a 1 by 1 matrix, which is just a polynomial of degree D. And then you sort of inductively knock down the degree of the coefficients of the matrix that is determined of using lemmas 1 and 2. So I won't read this all out. I think we've explained it. All right, so that was a nice lemma. I just was a sort of loose end from last time. Now the main topic of today's lecture is Waltzman's theorem, which is sort of half of this theorem, which I've stated here, the Waltzman-Master theorem, which is, suppose I have an m by n matrix of logarithms of algebraic numbers, and suppose that the rank of this matrix is less than m times n divided by m plus n, then I want to know that there exists a change of variables on the left and on the right, such that I can write this matrix as having a large chunk of zeros in the upper right-hand corner, a block of zeros. Okay, so rational change of basis, so sort of matrices in SL, M, Q, or Z, it doesn't make a difference on the left and on the right, so that I could get this block of zeros here. Okay, and how big is that block of zeros? It has dimension m prime times m prime, where kind of the proportion of the rows plus the proportion of the columns that you get is greater than 1. So it's a pretty large chunk. Okay, so what is, and so why does this theorem fit into our topic of this conference so well is that it's proved using auxiliary polynomials. So the Wall-Schmidt half of this proof is the existence of on auxiliary polynomials. So the question now is, what type of auxiliary polynomial do we want to produce? Okay. So our matrix that we're starting with, say Aij, these elements are logarithms of algebraic numbers. So let those algebraic numbers be xij. So they're the exponentials of the Aij. Okay. And we're going to consider a subgroup of q bar star to the n, right? So we're starting with an m by n matrix. So each row here is a vector in q star to the n, okay? And then you can then you just take the subgroup generated by all of those row vectors, okay? The subgroup generated by the m rows, okay? And that's what we're going to call capital X. And then, sorry, this is, I don't know why the star here came down. This is just supposed to see upper star to the end. Okay. And then just like we saw in the previous talk with the similar notation, we let x of n now, so this, we let x of n be the set of elements in this group x, that are given by this box of size n. So you take sort of the product of the first row to the a1 power times the second row to the a2 power, all the way up to the last row, the mth row, to the amth power, where each ai is between 0 and n. Okay, so this is some box. If there's if there's no dependencies somehow, that's kind of the point of this, is that you want to construct a polynomial that shows there are dependencies. But if there's no dependencies between these elements, then somehow the number of the size of this set, I guess, would be n to the m. Capital N to the little m. Okay. So now, here's Waltzman's theorem. So Waltzman's theorem is the existence of an auxiliary polynomial. Okay, so Waltzman's theorem says, okay, so suppose we're in this situation where the rank of this matrix of logarithms of algebraic numbers is small. So suppose the rank is less than m times n divided by m plus n. Then there exists an epsilon greater than 0, such that for all capital N sufficiently large, there is a polynomial with integer coefficients and whose degree is less than n to the little m over n minus epsilon, and that vanishes on all these points. So as I mentioned, if these were completely generic, the size of, so if generic, if I took random complex numbers, then the size of x to the n would be n to the m, okay? And the number of coefficients of my polynomial p, well, it has degree n to the m over n minus epsilon, and it has, it's a polynomial in n variables. So that means the number of coefficients, for me, degree is remember, it's the maximum maximal exponent in each term. So in each ti, it's the maximum exponent ti. So it's very simply just this quantity to the nth power. So this would be n to the m minus n epsilon. Okay. Oops. Oh, okay, good.
Show me.
Yeah.
Could you clarify what you mean by x sub I to the a sub I, since x sub I is a vector?
Yes, thank you. I mean each element to that power. So yes, this is going to occur often where I kind of take a vector to a power, and maybe it'll even get worse later. So this means like x sub I1 to the a I, comma x sub I2 to the ai.
Okay, thank you. And then when you multiply the
and then when I multiply component wise. Yeah.
Okay. Okay.
Yes.
All right. I have to wrap my head around that. That makes a lot of sense.
Thanks. Yes. Yes. Apologize. It's not the, yes. I'm trying to save notation, but at the expense of clarity, apparently. I apologize. Yeah. So that's what this means. Okay. That's what this one term means. And then what does the product mean? It's component-wise multiplication of vectors. So that's why I kind of wrote it as being a subgroup of sort of C star to the n. So we're sort of multiplying in this group. This is just the product group. Okay.
Thank you.
Yeah. Yeah. Sorry about that. I should have clarified that. It's very unclear. Okay. Right. So what I was saying is that the number of elements of this box is n to the m, if completely generic. But the number of coefficients that we have in our polynomial that has all these elements as roots is fewer. Okay, it's n to the m minus n epsilon. So n epsilon is greater than 0. Okay, so what this means, right, is that you're saying that some matrix has small rank. That is, if you do just like in the last talk, and just like right, and by last talk I mean both Heath Brown's talk earlier this morning and my last talk. What this means is if you arrange the monomials, right, that are defining this polynomial, evaluated at each of these points, if you make a matrix out of this, that means that that matrix has small rank because sort of less than it, right? You're having a polynomial. So you're saying that there's sort of the coefficient of the polynomial are in the kernel of this matrix. So you have a matrix, a polynomial that has more roots than it should, right? Okay, so you don't expect such a polynomial to always exist. You have to have some assumption, and of course, this is where you're using the assumption of the theorem in a big way, that this rank is small. Okay, and so here is Michelle Waltzman who proved this theorem. Okay, and I'm not going to prove this one today, but I'm just going to tell you Master's theorem picks up where that theorem leaves off. Okay, so Waltzman and Master had 2 papers. I think there are maybe consecutive in the same volume of Mentionis proving this result. So Waltzman's theorem is the previous one, and Master's theorem is this one, and it picks up where the other one leaves off. So, and Master's theorem is something purely in algebraic geometry. So you start with any field of characteristic 0, and you take a matrix of elements, non-zero elements in that field, and you define this box x of n as before. Now let's define a pairing on z to the m cross z to the n into k star using this group x, which is the product of xij to the power of ai times bj. So this is a bilinear pairing, okay, on z to the m cross z to the n into k star. And Master's theorem says, okay, now suppose there exists a polynomial that Waldschmidt's, there's no matrices and logarithms anymore. This is a purely algebraic statement. So Master's theorem inputs the output of Waldschmidt's theorem, which is this auxiliary polynomial. So let's say it has degree, and so you don't even need as small as n, capital N to the m over n minus epsilon. You just need less than a constant factor of n, capital N to the m over n, and namely the constant factor of little n to the m over n. Okay, so if it has small degree than you expect, such that it vanishes at all x in x of n, then there exist subgroups, and not just subgroups, but big subgroups of size of rank m prime and n prime respectively, that are orthogonal with respect to this pairing. Okay. And of course, saying that you're equal to 1 here, if you take the logarithm, that's saying that the logarithm is equal to 0. So it's very easy to translate this into the conclusion that I gave about the change of bases matrices on the right and the left. It's you choose bases, for your z to the m and z to the n that start with bases for a and b respectively. And then when you write down your matrix in that respect to that basis, you're going to get a big block of zeros in the logarithm matrix. Okay. So it's a simple exercise to deduce the statement of the Waltzman-Master theorem that I made from this combining Waltzman's theorem and this theorem of Master. So you can see this is a purely algebraic statement. Somehow there's no logarithms anymore. It's that the existence of this auxiliary polynomial gives us the result that we want. Okay. Are there any questions so far? Okay, so what I'm going to do for the rest of today is prove Waltzman's theorem. And I told you I wasn't going to do anything p-adic, but I hope you'll indulge me for just 5 minutes to do something p-adic. I'm going to actually give 2 proofs of Waltzman's theorem. And the first one is not going to be complete, but it's going to give sort of the flavor of it, and that's going to be p-adic. It's easier for me to think about this proof p-adically. So let me just take 2 or 3 slides and do a p-adic proof of Waltzman's theorem, and then I'll do the complex case and more generally. So so here's the theorem. This is Waltzman's theorem. Now everything's p-adic, so we're going to have p-adic logarithms of algebraic numbers. Okay, so suppose we have our matrix whose rank is small, less than mn over n plus n. You want to prove that there exists a polynomial, the integer coefficients, that has degree less than you'd expect in order to have vanishing on all of these points. Okay, so because this is just sort of some intuitive, trying to impart some tuition, I'm going to allow myself to make some strong assumptions. So I'm going to assume that the xij are integers and that they're 1 mod p. This will basically this can be, we've seen that going from integers to algebraic numbers is not too hard. There's 2 steps involved. One is clearing denominators, and the other is taking norms down to z. So this isn't actually that much of a loss. It just makes the notation easier in this kind of simplified proof that I'm giving. And xij being equal to 1 mod p. Of course, this is also easy. P-adically, you raise the xij's all up to some power, you can make them all 1 mod p. So that's not too hard to obtain. So this isn't really a loss of generality, even though it might seem so. Okay. Anyways, so this rank, this matrix has rank R. So that means that some n minus r columns are in the sort of QP linear span of the first r columns, because this is a matrix of coefficients in QP, this field, and it has rank R. So that means that there's some r columns that all the other columns are a linear combination of those. So let's move all those, the linearly independent ones to the front and the linearly dependent ones to the back, and then we'll and I'll just sort of scale the rows. This doesn't change much, such that all the coefficients appearing in those linear dependencies are in ZP rather than just QP. Okay. Then, so what that means is that sort of the last so n minus r columns are linear combinations with these coefficients in ZP of the first r columns. So those are logarithms. So when you exponentiate, that means that for any elements in this group X, we have for any element that its coordinates, right? These coordinates, right? So these elements of X are just products of the rows of my matrix when I sort of exponentiate the matrix of logarithms. So I take the exponentials of all the elements of the logarithms. So I get the algebraic numbers themselves. Then these elements X are just, the various products of the rows, the first row to some power, the second row to some power, blah, blah, blah. And in each row, right, we're saying that the last columns are linear combinations of the first R column. So that means that for any element in my group X, the last n minus r components of this vector can be written as a product of the first R components to these lambda I powers. And these are, some powers in ZP. Okay, and you can see why I wanted my xi's to be congruent to 1 mod p, because then it's well defined what it means to raise an element that's 1 mod p to a power in ZP. Okay, so we expand this as a power series. So what does that mean? Well, the function z to the lambda, if z is congruent to 1 mod p, you can expand this as a power series, as we're thinking of z as 1 plus z minus 1. This is now divisible by p. And then you expand this using the binomial theorem with an infinite sum of lambda choose I times z minus 1 to the I. This converges for all z that are congruent to 1 mod p. Okay. Okay, so now this thing that's sort of divisible by p, we're going to consider that variable, we're going to call that ui, so sort of a change of variables. And then we consider the map that takes a polynomial in t1 through tn. So first you replace ti by 1 plus ui, and then you send it to a power series. So, okay, so first of all, it's just a polynomial, not just a power series. It's just a polynomial in u1 through un. But then we mod out by the fact that sort of ti is a product of the previous ti's to lambda I power. And this really is t. So the point is that for this t minus 1 here, you plug in the u, and you expand this, you get a power series in u. Okay, so this is maybe looks funny the way I wrote it with u's here and t's here, but this is correct. This is just using the fact that this can be expressed as a power series in the u's. Okay. And then this power series has a very special form. I mean, it's just of the form ui equals something, right? It's just this. If you write this as a power series in the ui, it's ui equals a power series in the previous uj's, j going from 1 to r. So that just says I can basically knock out the last n minus r ui. So this as a ring, as a ZP algebra, is just isomorphic to ZP adjoined the first R variables, right? What I'm saying is that the last n minus R variables are dependent on the first R. Okay. So you consider this map. So given a polynomial, maybe with integer coefficients, we can always map it in here, and we get a power series in ZP now, right? But then there's fewer variables. So now, if for some integer c, your polynomial has image in here, that's a power series, such that the coefficients of any monomial of degree less than c is divisible by p to the c, then p will be divisible by p to the c for any z and x, right? Because for any z and x, the evaluation of p at z1 through zn sort of factors through this map, because the last n minus r coordinates of z, it's what I was saying here, exactly satisfy this relationship with the first. Okay, so I can sort of evaluate it by evaluating it here by whatever power series I get here and plugging in ui equals, zi minus 1. Now zi minus 1 is divisible by p. So if all the terms with degree greater than c are going to be divisible by p to the c, because I'm plugging in a ui that's divisible by p. So if the degree is at least c, then p to the c, that's going to be divisible by p to the c. Okay. And if I look at, I'm assuming that all the coefficients of the polynomials of degree less than c are divisible by p to the c. So of course, those are divisible by p to the c. And if I sum a bunch of numbers, even infinitely many p-adic numbers that are divisible by p to the c, then their sum is divisible by p to the c. And this is one reason why I like the p-adic numbers. You can't necessarily sum a bunch of infinitely number of complex numbers that are small and still say that it's small, obviously. Okay, so this number will be divisible by p to the c. Okay, now how many coefficients are we worrying about here? Well, they're all the ones of degree less than c, and because of my simplistic notion of degree, the number of such coefficients is just c to the r, because there's r variables. So now we're using the fact that r is less than this n, right? So it's c to the r rather than having to worry about c to the n, right? I could have done the same trick somehow from the beginning, but I wouldn't have gone very far, because I would have had c to the n variables, coefficients here, instead of c to the r. Anyway, so the number of possible tuples, if I imagine assembling, right, all these coefficients into a tuple, there's c to the r coefficients, and their value modulo p to the c. I want it to be 0, but their value mod p to the c, there's p to the c values of that. So the total number of tuples of coefficients mod p to the c for all the coefficients I care about is p to the c to the r plus 1. Okay, and so now we're going to do some pigeonhole argument again, where we say we have more pigeons than we have holes or boxes. So the pigeons are the polynomials. So how many polynomials of degree less than d that you have of height h, so say with non-negative coefficients, less than h, that's of course h to the d to the n. So by the pigeonhole principle, we'll have two polynomials that land in the same box if h to the d to the n is greater than p to the c to the r plus 1. And if that holds, then the difference of those two polynomials, the two distinct polynomials, the difference will be a non-zero polynomial that then has my property that it's, when I evaluate it on any element of the subgroup, it's divisible by p to the c. Okay, so this is one inequality that we want. And now we want to use the fact that integers, when they're sort of small, are 0. Oh, did it not advance?
Yeah, I don't think we saw you scroll down.
Oh, so you missed the whole previous slide. It's just weird that it just decides to all of a sudden. There we go. Sorry, so I should probably repeat the slide since you didn't see me. So the number of polynomials of degree less than d with non-negative coefficient less than h is h to the d to the n. And those are my pigeons that I'm fitting into these boxes of what they can reduce to under this map and then coefficients mod p to the c. So I want more pigeons than boxes. So h to the d to the n greater than p to the c to the r plus 1. And the difference of two such polynomials will land in the same box and give you the polynomial we're looking for with height at most h, and non-zero polynomial height at most h, where I evaluate on every z, it's divisible by p to the c. Okay, so now we want to use, so this discreteness of the integers takes on a slightly different form in the p-adic setting, which is you say that a number can't be more divisible by p than its Archimedean size. That is, if an integer, so before we use the fact there's no integers of absolute value less than 1 other than 0. Now we're going to use a slightly modified version of that, which is that there are no integers divisible by p to the c of absolute value less than p to the c other than 0. Okay, so we're going to show that the divisibility by p is greater than the Archimedean size. So how large can p to the c be? Well, okay, there's some constant you need to input, which is the maximum absolute value of any of these x ij's. Then the z's, so the element, this is sort of a component of a tuple in this group x. If I go up x to the n, well, each x ij is at most n, and then right, and then I'm raising them sort of to the nth power, so I get m to the n, and then I have m rows, so I can multiply m of those things together, so I can get another m power here. Okay, so the size of a polynomial of degree degree d, well, it will be, you're raising each of these. So the exponents can be raised to the dth power, so you raise to the dth power, and then you have n variables, so you multiply them all together, so you get another n. So you get dmn here. And then the coefficient has height h, and then there's d to the n monomials, coefficients that you're adding together, so you get a factor of d to the n. So here is your absolute value, the Archimedean absolute value. Okay.
So I mean, if
therefore,
sorry, are you circling things because we can't see that?
Great. So now that's not working. Wow. Okay. Yeah, I am circling things, and it's too bad it's not showing up. At least you're on the right slide now. I can sometimes, if you toggle this, it wakes up. Yeah. Okay. There it is. So I was just circling the stuff I've written. It wasn't very helpful, I think. I was just saying, yeah. So I was kind of trying to explain term by term where these are coming from. Hopefully, it's clear that it's just the naive estimate. There's nothing deep about this at all. Okay, so therefore, like I said, if the number is divisible by p to the c, but its absolute value is smaller, is bounded by this, and p to the c is greater than this, then it has to be 0, right? Then it has to be 0. Okay, so now you need two inequalities. You need h to be large relative to c to satisfy this, and you need c to be large relative to h to satisfy this. Right, so they're kind of pulling in opposite directions. So, okay, so now the degree that you want is n to the m over n minus epsilon, and we're going to write h just so that these can be compared easily. We'll write it as p to some lowercase h, and then the inequalities become inequalities in the exponents because everything is p to a power. Then this inequality becomes this. Okay, so h times n to the m minus n epsilon is greater than c to the r plus 1, and then this says c is greater than something plus h. So again, these are kind of pulling in opposite direction. H wants to be bigger than c, but then c wants to be bigger than h. Okay, and then so sort of I've sort of take this capital M, lowercase m, and lowercase n here just become sort of sucked into some constant here. Okay, so the k prime is the constant. Okay, so now we just sort of look at this inequality and we see, okay, so I'm going to make C to be, what's the biggest term here? The biggest term here is this one. So I'm going to set C to be n to this power plus something small. So I just take the minus epsilon and make it a minus epsilon over 2, and I set C to equal that. Then that will make this bigger than this. This is already smaller, so we don't have to worry about it. And then to make C bigger than H, I'll make H to be C times n to the minus delta. So just make it a little bit smaller. And then this inequality is satisfied. Then I plug in these two equalities into this inequality and see what we get. You get some comparison of exponents, and you work out the inequality, and you get exactly something that's satisfied, the existence of an epsilon and delta satisfying this if and only if r is less than mn over m plus n. Okay, so that's kind of my intuition. So if r is less than mn over m plus n, we can find epsilon and delta greater than 0 such that all the inequalities in the previous slide are satisfied. Okay, and so that's the sort of whole proof of Waltzman's theorem in this simplified p-adic setting. So I should say Waltzman proved his theorem in both the p-adic setting and the Archimedean setting, and the proof is something on the along the lines of what I just described. Okay, now I want to give a different proof, and I'll focus on the complex case because I think that's what most people are sort of familiar with. And again, this uses determinants. So this is hopefully very much in line with the lecture series of Heath Brown. Okay, so the idea is we'll view the existence of the desired polynomial as the solution of a linear system and show that the associated determinant vanishes. And so this idea in transcendence theory is called the theory of interpolation determinants. All right, so consider the matrix whose rows are indexed by these elements, z and x of n, that I want to be my roots of my polynomial, and whose columns are indexed basically by the exponent vectors of polynomials of degree at most n to the m over n minus epsilon. It is zn of that, right? So tuples of n tuples of integers where each element, each coefficient is bounded by this. So these are the exponent vectors of the monomials in the polynomial that I want to make. Okay, and so then I make a matrix that I call L, which is z to the y, right? So each row of this is the set of monomials of degree up to this quantity evaluated at my z, right? And so if I multiply that by a vector, then that gives me the value of the corresponding polynomial evaluated at that z. So what we want to show is that the rank of this matrix is small. Okay, it's less than its smaller values, so that this matrix does not have its maximum possible rank. It has something in its kernel, because that vector in its kernel is going to be the set of coefficients of the polynomial that I want. Okay, so I want to show this. All right, so this is an idea that I think we've seen in several talks. So, how am I going to use the fact that the rank of the logarithm matrix is small, right? So there's two matrices floating around now, this big, huge interpolation determinant, and then this small m by n matrix of logarithms. So how do I use the fact that the rank of this logarithm matrix is small? Okay, so this is a nice interpretation of rank. I don't think I ever saw this when I learned what a rank was in a linear algebra class, but it's kind of cute, which is that the rank of a matrix is equal to R if there exist m vectors, which I'll call beta, and n vectors, which I'll call gamma, with in k to the r, such that aij is the dot product in the usual, dot product in k to the r of beta I gamma j. I mean, this is basically just saying, I guess I kind of did see this, because it's basically just saying that the m by n matrix can be factored into an m by r matrix and an r by n matrix. And then you're just taking the rows and columns of those matrices and calling that your betas and gammas. Okay, and so applying this to our situation, we have a matrix of logarithms. And since its rank is equal to r, what that means is that we can write log of xij as the dot product of beta I times gamma j for some vectors, beta I and gamma j in c to the r. And as before, I hope this doesn't cause too much confusion. Right, so beta I, each beta I is a full vector, okay? Beta I is a vector and gamma j is a vector with r components. Okay, and so if I have my z's, remember what my z's are in this confusing notation. So x1 through xm are these rows in c star to the n, and you're looking at elements in this box. So if I have some element which I call z, then I can think of this element z to the y, these elements that make up the components of this big interpolation matrix that I talked about on the previous slides, that I can write this as the exponential of the dot product of sum of beta I li and sum of gamma j yj. Okay, so right, this is just working out the fact that log of, you just plug these in, calculate this, and plug this definition in, and you'll get exactly z to the y. Okay, so that's what we're going to use. So interpolation determinants are very generally, so what we're going to do is we're going to think of as the function, as an analytic function, e to the power of something dot this fixed vector. So we have a bunch of analytic functions. For each y, I have an analytic function that sends, so analytic function in r variables that that sends a vector in c to the r to e to the power of that vector dot this fixed vector. Okay, and interpolation determinants are matrices, or determinants of matrices that arrive from applying analytic functions at certain special values. So let me now say that. Okay, so before I do that, let me remind you about Schwarz's lemma. So we're going to use this to prove the theorem on interpolation determinants. I stated this in the first talk when I was proving Baker's theorem. Baker's lemma was a generalization of this. And so this is Schwarz's lemma from complex analysis. So if you have an entire function with a 0 of order greater than or equal to t at 0, then there's a bound if I have sort of, if I have nested circles, then there's the bound on the value of the function on this circle in terms of the value, on this disk. I should say disk, not circle. On the value on this disk in terms of the bound on the value of this disk, with a factor of little r over capital R to the power of t. Okay. All right, so I think this is very familiar, so I'm not going to prove this. The proof is the same as what I did for Baker's lemma. You take your f and you divide it by z to the r, z to the t, and you say this function is entire because we have our derivative, and then you use the maximum modulus principle on that function. Okay, so that's the very quick summary of the proof. But now let me give the theorem on interpolation determinants. So again, I have a sort of nested radii, but I'm calling it capital R prime and R. I shouldn't have called the other one little r on the previous slide because my little r here is my fixed rank, right? So shouldn't reuse variables. But anyway, so I said interpolation determinant is the determinant that you get by taking determinant of a matrix whose columns are indexed by analytic functions, okay, on c to the r, or at least on some disk in c to the r. Maybe this is called a polydisk. Is that the proper word for this? Where it's I'm bounding the size of each component, right? So it's like a box, okay. Then and if I have some elements, so I evaluate these d analytic functions at d points, okay, inside a smaller box inside of which the functions are defined. That's my determinant, okay? So the determinant is the columns are indexed by functions, the rows are indexed by points, and then I evaluate the function at the point, okay? And I take the determinant. That's the definition of an interpolation determinant, okay? And what's amazing is that there is very generally, there's the bound on the size of such determinants. So such determinants actually want to be small. Okay, and we'll explain why. And this, at the heart of this, is the Schwarz's lemma. Okay, so the bound is capital R over little r prime. So R is sort of the bigger ball on which the functions are analytic, and R prime is the ball on which the points that you're evaluating actually live in. There's some exponent, which I'll explain what it actually is later, but I'll just say that there's a lower bound on it, which we'll use. Okay. And so this d factorial just comes from, permutations in a determinant. And this is the absolute value, so the maximum size of any of these each of these analytic functions on this larger disk. So somehow it's like Schwarz's lemma. If you have a bound on the function on a big disk, then you get a bound evaluated at these points inside the smaller disk with a big factor that's dampening you down. That's damping you down here, right? So this is some number greater than 1. You're taking 1 over it, and then this exponent is very big. Okay? Hopefully it's large enough in your preferred application. Okay, so here's Michel Laurent, who introduced this idea in the applications of these ideas in transcendence theory.
So, mate, about what time was this happening?
Oof. I'm going to need to get back to you on that.
Sure, yeah. I'm just
in the last century, for sure.
Okay.
In the later parts of the last century. Now, whether it was 80s or 90s, I'm not sure. I think 90s. I shouldn't put myself on the spot. I'll look it up and get back to you.
That's interesting because Bobby Aripila is about the 90s, and then Heath-Brown's Annals paper is 2002 by the time it was.
Yeah. So this was I could be wrong, but I'm rather confident it was in the last century.
Okay, thanks.
I'll get a date for you on this paper. Okay, so here's the proof for that theorem on interpolation determinants. So that you view this determinant that you're interested in as the special value at z equals 1 of an analytic function, which is you just stick a z in there. So we're making an analytic function of one variable, which in this determinant to care about is fj of zi, and I just stick a z in there. Okay, and then the fj's are all analytic up to variables of size r. So the zi's have absolute value less than equal to r prime. So this is analytic up to r over r prime. Okay. So the punchline is this function, this analytic function, has a 0 of some order, which I'm not telling you yet. I'll tell you in the next slide, which I'll call you. We'll discuss the order of it, and we'll have some large order, which I'm calling theta sub r of d. And then the result, once you have that, then the result just follows from the Schwarz's lemma. So as I said, L is just delta of 1. And so its absolute value is bounded by r over r prime to the negative the number of zeros, the order at z equals 0, times the maximum absolute value of this delta on the disk of size r over r prime. And now we use the purely naive upper bound, the trivial upper bound. This is a product of fi's evaluated at points of on the disk of size r, and then you multiply those all together, right? That's how you think of determinant as a sum of over the permutations of all the ways you can traverse the matrix, and so you get this product, and then there's d factorial such permutations, so you add them together. So this is the most naive, simplest, most basic upper bound you could get. Okay, and then you just plug that into here, and that's exactly what the theorem was that I stated on interpolation determinants. So what we need to do is really understand what the order of the 0 of this function is at z equals 0. Okay. So now we write each fi as a power series in some variables. So we'll call it ui. I don't want to call them z because these are my actual numbers that I was plugging in, or my tuples of numbers that I was plugging in. So we write each fi as a power series in the variables, which I'll call u1 through ur. Okay. And by multilinearity of the determinant, it suffices to consider the case where your fj is just a monomial. right? So each fj is a sum of monomials times some coefficients. But of course, determinants, that right, the way the interpolation determinant is written is that entire column is given by that that Taylor series. So I can break it up into a sum of the determinants where I just take each monomial one at a time. So it suffices to show that if I just have monomials, then I have this order of vanishing. Okay, so write each fj as a monomial. So it's u1 to the some exponent times u2 to some exponent, ur to some exponent. And this vector of exponents, I'll just call vj. Okay, so then, now remember what happens. How do you define the function delta? You just take, instead of evaluating at zi, this function, you evaluate at zi times z, right? So what happens if I scale these all by z? I just get z to the power of the sum of these exponents. And that sum of the exponents is what I write here as you know, norm or double line of vj. This is the sum of vij. Okay, so that just pulls out. Okay, and then that's true for each column. So then you pull that z to the power of the norm of vj for each column. So then you get z to the sum, right? You get z to a sum of each of these. So this is the order of vanishing, you see, of this term, at least this. Okay. Now, if any two of your tuples are the same, then this matrix, you know, what's left is what you get when you plug in the zi's into this. Then this matrix has two columns that are identical. So it's determined to 0 if any two tuples are the same. So this is 0 if any two tuples are the same. So what you need is distinct tuples. Okay. So what is the definition of theta r of d? It's the minimum of this sum as vj ranges over all distinct tuples of n to the r. And this n is, I apologize, this should be a bold n. This is the natural numbers. And I mean the French natural numbers, not the American natural numbers. So start including 0. So, right. So just to give you a simple example of what I mean by this, if r was 1, then I would need d distinct numbers. So I would have 0, 1, 2, 3, all the way up to d minus 1. And the sum of those is d choose 2. So, right, so theta, so example, this is sort of the only one you can sort of do, or not the only one, but you can do in your head, the first one you can do in your head, this is d choose 2. Okay, I hope that was clear. So because then these vj's, there's not vectors anymore, r is 1, so these are just numbers. I'm saying I want distinct numbers, distinct natural numbers, and I want d of them. So the smallest their sum could be, if I have d distinct natural numbers, the smallest the sum of d distinct natural numbers is d choose 2. It's 0 plus 1 plus 2 all the way up to d minus 1. Okay, so you can see that this is growing as basically like d squared. Right? In general, it doesn't grow as fast as d squared, but it grows as fast as d to the r plus 1 over r times some constant. Okay, and so for this inequality, so this is a purely combinatorial thing. Since I don't have time, I'm going to refer you to Waltzman's book, Linear Independence of Logarithms of Algebraic Numbers, which is really available on the internet. Lemma 3.4, he proves this inequality. Okay, so now we can finally do proof 2 of Waltzman's theorem. So we have this matrix L, which is the matrix of this very huge matrix of zi to the yi, and we want to show that for any square matrix of size n to the m minus n epsilon, that the determinant of that matrix vanishes. Okay, so z1 through zd. So this is an interpolation determinant. So z1 through zd are indexing the rows. The y's are going to be indexing the columns. The y's are just elements of this box. Remember, these represents the monomials in our polynomial. And as explained earlier, the entries of this matrix, the zi to the y, we can think of that as this function, e to the power of sum of beta I li, where the li corresponds to the z, right? And the yi is the y, right? So the y, this y is a vector y1 through yn.
Shomi, can you remind me, we used to think of the degree as being m over n minus epsilon. Can you remind me why we've multiplied the exponent through by n and the size?
Did I make a mistake? No, the degree is still m over n minus epsilon, but the number of such monomials will be the degree to the power of n.
Okay,
right,
thank
because
you.
there's n variables, right? So the number of monomials is this, but the degree is still m over n minus epsilon. Yeah.
Okay, thank you.
Okay. Right. So this number is the size of the set. Yeah. Okay. Right. And then for each y, we have this analytic function, which just takes a vector in c to the r and dots it with, this vector in c to the r that's corresponding to this y. So again, the notation is trying to be very condensed. This is a vector of integers of size n. Each gamma I is a vector of complex numbers of size r. So when I'm wait, what? Right, and yi, so yi is the component of this vector. So this is just a vector of size r, and I'm adding n of them together. So maybe it's clear if I say this is I equals 1 to n, right? Okay. All right. All right. So now what can we say about the size of the determinant? We want to show this determinant to 0, right? That's our goal, and then we'll be done. We'll get the matrix as rank less than what we want. So you apply the theorem on interpolation determinants to bound the size. So, all right. So let's look at the size of how big the u's can be. Well, these beta i's are just some constants, some universal constants, and li is going up to n, right? These are in the box of size n. So the ui's are bounded by n times some constant. Okay, so that's going to be my r prime in the application of the interpolation determinants theorem. Okay, and then we're just going to let r be anything bigger. It doesn't really matter. So we'll just take 2r prime. It doesn't, because we're just going to use a naive bound on the size of this. These are entire functions. They're analytic on the whole, c to the r. So it doesn't really matter what we take. And we're going to use a naive bound on this, so it doesn't really matter. So we'll just take 2r prime. The point is that the absolute value of L is then 1/2. Okay, it doesn't really matter. It's just something less than 1 to some exponent power. And remember, I said that theta r was basically some constant times d to the r plus 1 over r, and then you get d factorial and the naive bound on the size of these analytic functions. But we can figure this out very easily. If a is the maximum of the absolute value of my original algebraic numbers xij, then each c to the y that I have in my matrix is bounded by what?
Sorry, Shomi, I think it froze again.
Froze again. Thank you for telling me right away. Hope it's okay if I go a minute or two over, because I think I've lost that much time in this freezing. So, right, the size of each of the coefficients of this matrix is at most, the maximum that this can be to the nth power. That comes from the fact that z is in the box of size n with these things as the generating set. So it'd be a to the n. And then I'm looking at monomials of degree this, n to the m minus n epsilon. So I get raised to this power. And then that's for each individual coordinate. And then I have n coordinates that I'm multiplying together. So I could get a constant factor of n here. This n is kind of irrelevant because it can get sucked into the a. It's just a constant. And therefore, the absolute value of fi of my analytic functions that I defined previously on this disk of, or this polydisk of size r is at least, okay, so what is d? D is I'm sucking in the n into the a, and I'm also, my r was twice the radius of given by the x's. So this would be, a to the 2n. So make sure, square the x's would be the absolute maximum absolute value on this disk. But it's just some constant, so it's okay. And so it will be that, each fi sub r will be bounded by d to this power. This is just this, where I've sucked in the n into the a, and since I went to a larger radius, then I have a factor of 2, and I suck that all into my d. And then there's little d of them, so I raise it to the dth power. Okay, and remember what little d was. What was my little d? That was the dimension of this interpolation matrix. So that was n to the, this is what Lillian was asking about. This is m minus n epsilon. Okay, and so if you put that in here, sort of combine terms, then you just get this. So, and again, so as you notice, I'm not caring too much about what this base is. Just like I took the base of 2 in the dampening factor, it doesn't really matter what the base is in the growth factor, because what matters is the exponent, right? If one exponent is larger than the other, it doesn't matter what the bases are if they're constants. Okay. Okay. So let me try to rush to them over time. This factorial is much smaller than what we just estimated this to be, so I can ignore it. If I can dominate this term, I can certainly dominate the factorial. We need to make sure we're dealing with integers here, so you can scale to obtain integrality. That just scales this constant d. I'll leave you that to check, which is, I mean, if these have a denominator, then you just multiply them all by d, but that just scales my absolute value. So if I scale with some denominator here, I shouldn't call it d. If I scale by some denominator to make this an algebraic integer, that just scales this a, that just scales this d. So that doesn't do much. If you take the norm, it's the same thing. You're just multiplying whatever the degree of the field is. You're multiplying a bunch of numbers of this size together. That's just, raising this to the power of whatever the degree is. So again, that just increases d. So both things that we need to make sure that we're dealing with actual integers just changes this factor of d, this constant d, which we don't really care about. So L will be 0 if this thing is going to 0 faster than this thing is going to infinity, right? Right? It doesn't matter. This is a 2 and this maybe is a big D. All that matters is the exponents. So what are the exponents? The exponents are d to the r plus 1 over r and this complicated thing in n. You plug in the definition of d, so you get both things in n, powers of n, and so which power of n will be bigger is just which exponent will be bigger. So you just write that out. This exponent is bigger than its exponent, and I'm a little bit confused about the directionality I have here. I feel like I want to say gray. This is a typo. This is greater. Okay. And this simplifies, yeah, which is good because you can see a 1 over r coming here, and then I get m minus n epsilon. I bring it to the other side. So yeah, I think this is right. So this simplifies to 1 over r being greater than this, which that inequality you can satisfy as long as r is less than mn over m plus n. All right, so if r is less than mn over m plus n, then I can find an epsilon satisfying this inequality, and I can prove that my determinant vanishes, giving me my desired auxiliary polynomial. All right, thank you, and sorry for going over because of these technical issues.